Okay, good morning to everyone. So today's class I'm going to discuss here two concepts such as so so these are the contents here I'm going to discuss. The first thing is alternative forms of pull-up and BiCMOS inverter circuit, right? So we need to discuss in detail concept of these alternative forms of pull-ups and BiCMOS inverter circuit. What are the problems we are facing in BiCMOS inverter in each state, and we can improve that drawback what we are facing in each concept, that is improving in our BiCMOS inverter circuit, right? And alternative forms of pull-ups. You know that in MOS inverter circuit there are two types of device. That is, one is a pull-up device and other one is pull-down device. But here we want to observe the uh, circuit operation and getting the how it is going to be perform the output response. We can change, we can replace the pull-up device instead of various devices. That's why he says it is a alternative forms of pull-ups, right? So let us start this two concept. So here, this is the first point here I'm going to take. Here uh, it is first thing is uh, this is the circuit here. Let us say this is the resistor as pull up here. This is one of the form of NMOS inverter circuit. Here it is, right? So this is enhancement mode device, pull down device, right? And this is nothing but pull up device. Okay, this is pull up device. So here I can use a resistor as a pull up device, and NMOS enhancement mode device is used as a pull down device. So now I'm going to discuss it is going to be perform as an inverter or not, right? So here let us see, here input is 0, input is 0. So then it is open switch. Open switch mode means it is in off condition, off condition. So then there is a connectivity availability in between VDD and Vout through this resistor. Then output is 1 or it is VDD, right? Okay, we can take this response as 1 or VDD. And similarly, in another case, that is, if you are applying 1 as input response, then this NMOS transistor is going to be on condition. So on means here the path is availability Vout to VSS. Okay, then whatever the response is available at the output side, that will be discharged to ground through this NMOS enhancement mode device. So finally we are getting the response is 0 voltage, 0 volts. Okay, so let us observe here, if you are applying input is 0, then getting output response is 1. If you are applying input is 1, you're getting output response is 0. So means it is performing the inverter operation when we are taking it as a pull-up transistor, pull-up device as a load resistance, right? But we can use instead of pull-up transistor as a load resistor here, there is a one problem here occur here, that is when we are going to be in fabrication processing techniques, it occupies excess area for the designing for chip designing process. That is a major drawback here when we want to take load resistor as a pull-up device, right? So let us go to this point here. Up to now, we have assumed that the inverter circuit has a depletion mode pull-up transistor as its load. There are, however, at least four possible arrangements here I am going to discuss. In first case, here it is load resistance RL. So this arrangement is not often used because of the large space requirement of resistor produced in a silicon substrate, or it is going to be in fabricating process technique, right? So this is the one of the drawback of when we want to take a load resistor as a pull-up device, right? Based on this requirement, we need to go another alternative form of this NMOS inverter. right? Second case, let us see here the NMOS depletion mode pull up, depletion transistor as pull up here. So here, when we want to go through another circuit here, this is the another circuit here. So here depletion mode, here it is called it as pull up device. Depletion mode transistor, here we call it as pull up transistor. Instead of we want to make instead of we want to replace pull up transistor instead of resistor, right? And let us observe the output response here again. If you are applying input is zero, right? Input is zero, then this one is going to be off condition because of it is enhancement mode device. Here already the channel is available, the connectivity is available between drain and source. Then the path is available. We need to V out. We need to V out here. So let us see here. This is x-axis. We are here. I want to take a V input, and y-axis it is taken as output response, that is V out. So initially input is zero. So here like this, initial input is zero. The NMOS is enhancement mode is going to off condition. Now there is a connectivity VDD to V out. So we are expecting output response is VDD. Output response is VDD, right? And let us see here. So this period of part is no current flows. No current flows means if there is a path in between VDD to ground, then only we are expecting there is a current flowing through these devices. Okay, that's mean that thing nothing but here it is given it as no current flows. And output response, that is VDD is available at the output side when we are going to apply input is zero. So means it is performing the inverter operation. In second case, if you are applying input is one, then the V input the enhancement mode device is going to be in on condition. Then there is a path in between V out to ground. So what are the responses available here that will discharge to ground through this enhancement mode? Finally, we are getting the output response is zero, right? So when we are applying one here, output is zero. So if you are applying input is zero, then output is VDD. Okay. So by increasing this input response, V input as one, then output is like this. This is the output response, right? Here it is. Theoretically, we are saying it as a zero, but practically there is a slight amount of voltage which occur at the output side. But it is non-zero output response, right? Non-zero means there is a very small amount of voltage available at the output side. Generally, we are saying it is output response is zero theoretically. So this is the inverter operation. And coming to this graphical representation diagram here. So here initially zero, this is going to be in enhancement is off condition. So we are expecting output response is maximum. No current flows because of there is no path in between source and drain. So we need to ground. If we are increasing this response zero onwards, it was going to be increasing onwards at certain point. So both are in resistive region. So partially non-condition. So then there is a path in between VDD to ground. Then the current flows through the device. So this is the response here. This is the response going like this, right? And after exceeding 1/3/4 of these, then complete this is going to in a saturation mode. It is in resistive mode, right? Then we are expecting non-zero output response, right? So coming to this point here, the first case, the power dissipation here is since rail to rail current flows when V input is logic 1. When V input is logic 1, so then the current flows through these devices. So logic 1 means here we are slowly increasing the input response 0 to some reaches to the 1. In between there is a flow of current is occur, right? Next case, that is B, switching of output from 1 to 0 begins when input is exceed the threshold voltage. Okay, so here the switching of output from 1 to 0 that begins when V input is exceeds the level, that level nothing but threshold voltage here. Okay, here I am going to apply input is 0, suppose 0 and 0.3 like that, and 0.5 and 0.75 and 1. These are the ranges here. So let us this is like VT. Suppose I want to assume here 0 to 0.3 is nothing but threshold voltage. If you are applied input voltage, that is V input here, V input voltage that will be exceeding this threshold voltage, then the enhancement mode device changing its conducting properties. Okay, so then the output response is begins starts to change from 1 to 0, right? Next, in third case, when switching the output response from 1 to 0, the pull-up device is non-saturated initially. So, and this present lower resistance through which to charge capacitive loads. So here, when that enhancement mode device is going to increasing its level, then it is decreasing its level. Means it is in resistive region. It's non-saturation mode. It is in saturation mode. It's a resistive region. Then there is a current path in between VDD to ground. Okay. Next case is NMOS enhancement mode as pull-up device. Okay. Let us see here. This is a NMOS inverter, NMOS device here. This is another NMOS inverter. Actually, it is also enhancement mode device. It is also enhancement mode device. But here, it is always on. It is always on. Why? Because VGG is fixed at VDD. VGG fixed at VDD. So we know that for NMOS for a MOS transistor, that is NMOS transistor, if we want to give the input response is 1, then the NMOS device is going to be on condition. So that is 1 here, VDD is 1, it is fixed. Okay, and here we want to apply input is 0, case is 1 and second case is 1. If applying input is 0, then this transistor 2 is going to be off condition. Already there is a connectivity in Vout to VDD, output response is VDD, right? And suppose if we want to apply input is 1, then the transistor 2 is going to be on condition. Yeah, already it is on. Now the path is available in between Vout to ground. Vout to ground here. So whatever the data is here, that will discharges to ground here. Finally, we are getting output response is 0. That is 0. That is practically non-zero, but theoretically we are saying here it is 0. And let us come to this graphical representation here. Let us observe here. There is just some drop occurs in output response whenever we are applying input is 0. That drop is nothing but VT1. We know that if your applied input voltage is exceeding that level is nothing but here it is threshold level. If your applied voltage is exceeding some level, some level is nothing but it is a threshold level. So when we are applying input voltage exceeding that level, then only the device is going to be changing its properties. So means even here we are applying VGS is VDD, there must be some voltage drop occurs, that is nothing but threshold voltage here. So if we are applying input is 0 here, but here there is some voltage drop occurs. But actually by applying this input voltage 0, we are getting response as VDD. But there is some drop occurs across this device. That is nothing but VDD minus VTD minus VT. Right? VDD minus VT. That is VT nothing but here transistor 1, that is T1. VT1. That much of amount of voltage drop by this from this VDD. That is the gap here. So this gap, when we are applying input is 0 here, then only this is the response that T1 VT1 is dropped by from the applied gate voltage here. That's why the output response is somewhat down from the VDD here, this point, right? And second case, that is when we are applied input voltage exceeding this VT2 nothing but threshold level 2 of this enhancement mode device, then only there is a path in between VDD to ground, then only the current flows through this device. This is the region here, current flows. And finally, we are reaching the input response is 1. The output is maximum output will be drops to this ground here. There is a 0 response, but practically it is not 0, right? So coming to the point here, first point, dissipation is high. The power dissipation is high since current flows when V input is logic 1, okay, and VG is returned to VDD, right? So Vout can never reach VDD. if VGG equal to VDD, as is normally the case. Okay, it never reached to the VDD because of there is a slight amount of voltage, that is some amount of voltage dropped by this from this VDD, nothing but it is VT1. Okay, next case. Point C, VGG may be derived from a switching source, for example, one phase of a clock, so that the dissipation can be greatly reduced, right? If VGG greater than the VDD, then only we are expecting the extra supply. Then an extra supply is really is required. Suppose we need to get the output response as VDD at the output side. So then extra supply is required to give this particular gate response instead of VDD. Then only we are getting without dropping this response, without response of this threshold level of pull-up transistor. Okay, extra supply is required here. Then only we are getting the maximum response at the output side if you are applying input as input side. So whatever it may be happening, it is performing the inverter response. Input is 0, output is VDD, and input is 1, output is 0. This is the NMOS enhancement mode as a pull-up device, right? Next case. So coming to the fourth case here, complementary transistor as pull-up. Complementary transistor means here it is nothing but PMOS device, PMOS enhancement mode device used as a pull-up transistor, right? And here NMOS enhancement mode device used as a pull-down device, right? So coming to this circuit diagram here, we know here input is 0, then NMOS is off condition, and PMOS is going to be on condition. Okay, now there is a path in between VDD to Vout. So we are expecting input is 0 here, that is here 0, then output is maximum, right? And this response, if you are applying input is 1, then NMOS is going to be on condition and PMOS is going to off condition now. Now the path is availability in between Vout to VSS because of NMOS is on condition and PMOS is going to off condition. The connectivity is disconnected between VDD and Vout through this PMOS transistor because of it is off condition. Now the path is available Vout to VSS. Whatever the data is here, that is discharges to ground through this NMOS transistor. Finally, we are getting output response is 0 for applied input voltage as high. That is the response here. Okay. In first case, that is 0, PMOS is on. So here this is, and NMOS is off. So that's why we are getting output response VSS is maximum here. And the second case, here V input is high here, and NMOS is on condition, and PMOS is off condition. That is the response here. So in between, but here we are applied input response 0 from 1. It not suddenly changes. It is slowly increases, slowly changing from 0 to 1. Okay. We are applying input voltages, that is V input is slowly varying from 0 volts to 1 volt. Okay, 0 to logic 0 to logic 1. So in this in this process, if your input voltage exceeding this threshold level, then the device both are in changing its conducting properties from on state to off state and off state to on state, right? At particular position, both are partially on and partially off condition. So at that connection, at that region, both are on partially. So then there is a path is formed in between VDD to VSS. Then we are expecting the current is maximum amount of current is flows through these devices, right? So this case is here. So both are going to be on condition, right? But another case here, output response is slow, drop down from VDD to 0, right? And here, this is the transfer characteristic circuit diagram graph here. And coming to the diagram C here, CMOS inverter current versus V input. V input versus current, right? So same thing here. Here in the region 1 and region 2, region 3, region 4, region 5. In region 1, here PMOS is on condition and MOS is off, right? Up to region 1, up to region 1, PMOS is, here P is on and N is off condition. So we know that there is no path in between supply rails, that is VDD to VSS. So means there is no current. Okay, there is no current. So that's why here the current is on a y-axis, V input is on x-axis. So there is no current here. That is slightly current. That is zero current. When this point, that is exceeding this level here, first case, then we are going to increase the input response, then slowly changing like this current. Okay, up to this region. Slight amount of current is going to be increases, right? Again, the input response is going to be increases. So then both are in on condition, both are in on region. So let's suppose this is the region here, right? 3 to third region. Here's the third region. So like here. So when we are input voltage exceeding this level, then both regions are, both devices are going to on condition. So maximum there is a when both are going to in on condition, there is a path in between VDD to VSS. Then maximum amount of current flows through those devices. So this is the current, maximum amount of current. Okay, and then it is going to be increasing. Then that current will be going to be decreases by increasing the V input response. This is the fourth case of alternative form of pull-up transistor. Okay, so here we can use PMOS transistor as a pull-up resistor, right? Let us go to this point here. No current flows either for logic 0 or for logic 1. Okay, similarly for logic 1 and logic 0, levels are presented at the output side. Right. Next, for device similar dimension, the P channel is slower than the N channel device. Okay. If your applying input is 0, then we are getting output response is 1. If your applying input is logic level 1, then we are getting output response is logic 0. So, and this is the current versus the V input response of CMOS inverter, inverter circuit, right? When we are using complementary devices as a pull-up transistor. Okay, right? Next, BiCMOS inverter. BiCMOS inverter. Here it is bipolar device and CMOS. Nothing but here the combination of CMOS and BJT. Nothing but BiCMOS inverter. So let us come to the circuit diagram here. So this is the transistor T2 and transistor T1 are nothing but bipolar devices, and transistor T4 and transistor T3 are nothing but CMOS devices. Okay, so this is the combination of circuit diagram, nothing but it is a simple BiCMOS inverter circuit. So firstly, I want to take it is going to be performing inverter operation or not, right? Firstly, here I am going to apply my input as 0 voltage here, 0 volts. Then it is T4 is going to on condition and T3 is going to be off condition. So if it is T4 is on condition, it is VDD connected. If it is on, these two terminals are acting as a short circuit. Okay, short circuit here. Then this is connected to the base of the transistor T2. Okay, again, when the base is connected to the transistor T4, then the transistor is going to be on condition. If it is on, the collector emitter terminals are short circuited. So whatever the data is available here, the data will be passes through this transistor T2. Okay, at the same time here T3 is going to be off condition, here it is going to be off condition. Okay, so whatever the where data is here, the data will be flowing in this case in this way, and where it is charging into this load capacitive load. So we are getting output response is 1. Okay, and second case, that is input is 1 volt, input is 1 volt here, then this is going to be off condition and this is going to be on condition. Okay, if it is off, this transistor is going to be off condition and this transistor is going to be on condition, right? If it is on, whatever the data is available in this load capacitor, that will be discharges to transistor T1. Finally we are getting output response is 0, right? Means if you are applying input is 0, then we are getting output response is 1. If you are in input response is 1 volt, then we are getting response is 0 volts. Right? Means it is performing the inverter operation. But here there is a one drawback. Okay, let us see the drawback here. Before going to drawback, we want to go through these points here. When designing with BiCMOS in mind, the logical approach is to use MOS switches to perform the logical function, and bipolar transistors are to drive the output loads. Okay, these are driver like it act as a drivers. Next, and second case here, it consists of two bipolar transistors T1 and T2 with one NMOS transistor that is T3 and one PMOS transistor that is T4, both being enhancement mode devices. Both are enhancement mode device. So coming to this point here, when V input is 0 volts, that is ground, T3 is off condition, T3 is off, so T1 is going to be not conducting. T1 is going to be not conducting. Okay. So then we are getting output response is 1 because of here T3 is off, and when we are going to apply V input is 0, T4 is on, T4 is on, T2 is on. That amount of voltage passes through the transistor T2 that will be charging in capacitive. So means in this case CL is charged. CL is going to be charged. Right? CL is going to be charged. In the second case, when V input is 5 volts, so here that is here applying here, then T4 is off condition and T3 is going to be on condition. Okay, so when T4 is off condition, T2 is also off, is nothing but non-conducting, and T1 is going to be conducting. So whatever the data is available at the capacitor, that will be discharged to this transistor T1. Okay, finally we are getting response is 0. Okay. But here there is one drawback here. If the transistor T3 is on, there is a direct connectivity. DC path is available VDD to ground through this transistor. That is the way here. So this is the way. This is not as a good arrangement to the BiCMOS inverter circuit. Okay. When you are applying input is 1 here, there is a direct path. There is a direct path is available VDD to VSS. This is the not a good arrangement for this inverter circuit. So we need to change this path. So we go for another alternative improving circuit, right? So before going to that, some of the disadvantages here. The advantages are nothing but it has a high input impedance and low output impedance, and it has a high current driving capability at the output side, but it occupies relatively small areas, right? And it has high noise margin. These are the advantages of BiCMOS inverter. And disadvantage nothing but the presence of DC path VDD to ground, that is through transistor T3 and T1. So this is the transistor T3 and T1. There is a direct path is VDD to ground. Okay, this is not a good arrangement. This is not a good arrangement to implement, since there will be a significant static current. There will be a significant static current flows when input is logic 1. So this is also a problem in that there is no discharge path for current from the base of either bipolar transistor when it is being turned off, right? So this will slow down the action of this circuit. Okay. So next go for the alternative form another circuit. This is an improved version of alternate circuit. So here the DC path T3 and T1 is eliminated, but the output voltage swing is now reduced since the output cannot fall below the base emitter VP of T1, right? So let us see here, that is here the DC path is disconnected. The DC path is disconnected here, right? DC disconnected, and again this path is going to like this. Now you can apply this input response 0, then it is going to be on condition, T2 is on. At this case T3 is off condition, T1 is off condition. it is on, then this is going to be charging the capacitor load. For V input is 0, we are getting response is 1. Similarly, V input is 1 here, so then it is going to be off condition, it is going to be on condition, it is going to be on condition. Now there is a path in between, like this, V out to ground through this transistor 1, then this will be discharged to ground. And here also one more problem is occur here. So here some of the response here going to be, some of the output is going, voltage will going to like this. This is nothing but voltage swing, output voltage swing. So voltage swing means the output response is going to be increasing or decreasing. It is going to, the output response is going to decrease or increase. That is swing, nothing but here. Swing means here swing, that is nothing but swing. So here some of the voltage going in this way here. So the transistor is, even the transistor is going to be turned off. That base current is not, the base current is not going to be decreases because of some of the voltage going to in this way. This is the drawback here. Okay, this is the drawback. So we need to protect the some of the swing voltage going to be in this way. So we need to be protect this voltage. Because of this action will be slow down this particular inverter circuit. Okay, so we need to go for another improved version of alternate circuit with the resistors, right? So this case, this is another improved version of alternate circuit with resistor. So here we need to connect the resistor R1 and R2 here. Okay, let us observe here. Again, we can apply the input response as it is performing going to be inverter or not. If it is 0, then T4 is on condition, T2 is on condition. So there is a connection here, collector to emitter. The current that voltage will be charging in this capacitive load. At the same time, it is going to be off condition. It is going to be off condition, right? If you are applying again in second case, if you are applying input is 1, this is going to be off condition, this is going to be on condition, and transistor T1 going to be on condition. Now the path is going to be like this. So output response is 0. Okay. If your input is 1, then output is 1. If input is 1 here, output response is 0. So here performing the output as it is performed as inverter operation. But here also one more problem is available here. When we want to go in fabricating processing technique in a chip design process, so the resistors are occupies very excessive area when we want to go in fabrication techniques or the chip designing process. So that is the drawback here. That is resistor R1 and R2 are having to large excessive area. That is the drawback here. So instead of that, we want to go with another improved version of alternate circuit. Instead of resistor, we want to make there is a MOS transistors, right? So before going to that, go to this point here. In this circuit, resistors provide the improved swing output voltage. When each bipolar transistor is turned off. Okay, transistor off, and also provide discharge path of our base current during turn off. Okay, the base current is going to be discharge path here. Okay, here some of the voltage swing will be protected here by using resistor R1. And next point here, the provision of on-chip resistors for a suitable value is not always convenient. It may be occupies a space consuming. It may be occupies a large excessive area. This is the drawback here. Okay. And next go for the to improve this version of BiCMOS inverter circuit instead of resistor. Okay, this is another improved version of alternate circuit with the MOS transistors. Okay, so here in this circuit, the transistor T5 and T6 are arranged to turn on when the T2, T1 respectively are being turned off. Okay, so generally we need to be discharge the base current path. So then we want to arrange with the resistors, but when we want to go with the resistors, it is to occupy very excess area in fabrication processing technique. So in order to reduce that disadvantage there, we want to go with another case. But basically, we want to provide the resistors to discharge the base current, to drop the to decrease the base current. So based on that concept, it is one of the drawback there. when we want to go with resistors to occupy very large space in the silicon substrate. Okay. Instead of that, we want to make transistors T5 and T6 instead of resistors here. Okay. Let us come to this point here. Suppose if you are applying input is 1 here, 0 here, then T4 is on condition and T2 is on condition, then the current will be growing like this, that it will be charged to the capacitor, right? And at the same condition, it is going to be off, it is going to be off condition, okay, and it is going to be on condition, okay. If even at any base current is available here, that will be discharged to ground if any swing is occur, okay. And something next case, it is going to be 1 here, it is going to be off condition, it is going to be on condition, it is going to be on condition. If it is on, this one is going to be on condition, right? If it is on condition, if any base current is available here, that will discharge us to ground here through this T5. And the second case here, that is T3 is on condition, T1 is on condition, right? T1 is on means that voltage will be discharged to transistor T1. Finally, we are getting response is 0. If you are applying input is 0, then output is 1. If you are applying input is 0, 1, sorry, input is 1, the output is going to be 0. And also there is a discharge of base current through this transistor T5 is for a base current discharges, decrease the base current of T2, and here T6 is decreasing the base current of T1. So then only the then only this action is going to be improved to decrease the base current of transistor T1 and T2. Okay, this is the final improved version of alternate circuit by CMOS inverter. Okay, thank you.